kind of chatting. So what this is about is I've been programming for a long time, and picked up Clojure about 10 years ago, or right when Rich went public, like 6 months. Loved Clojure, thought it was a big step forward in terms of language design and stuff. Rich has done a really good job of getting features that work well together and has an underlying philosophy. But I did embedded programming for 20 years. And so running on the JVM was just painful. So from the very beginning, I wanted a Clojure that would compile to C, or that would run on native stuff. And so, was it 5 years ago or so maybe? I kind of started part-time implementing that idea. And originally it was just a port of Clojure to C. And I kept tweaking things though. It's like, oh, Rich didn't really get this right. Because after you get 5 or 6, 7 years of experience using a language, you kind of learn the warts and stuff. And so I kept tweaking. It's like, oh, this is not right. I'll just do. So finally I decided, oh, this is just another language. This is inspired by Clojure, but it's not Clojure. So, and strictly for the back end, I had that was just what I was focused on. That's what I liked. Hadn't really given much thought. Actually, I still don't even know really how to do web programming. I'm learning now, but I'd always done back end or embedded stuff, and then this talk is about what happens when I discovered that I'm actually a front-end programmer by accident. And then some other things a little bit beyond that. So I don't know if you guys are here for the back-end part, the front-end part, or what. But so yeah, I've been working on this full-time. I quit my job 2 years ago to work on this full-time. And so learning to do web programming now to make some money to continue working on it. It's a whole new realm. I mean, back-end programming and web programming are totally different. And yet what's interesting going through this exercise is how some common things really are across both realms. And so that's kind of the background of the talk. I guess we have enough people here to get started, and other people can catch up as they come in. So, all right, cool. This is based on a true story. And I'm really relaxed in my talks. So if you have a question or anything, this is more of a conversation for me. So just shoot your hand up, pipe up, whatever, and we'll just talk about stuff. Okay. Programming languages. They are made to give instructions to computers. Pretty self-explanatory. We started with machine code. How many have done assembly language, like for real, hardcore assembly language? It's an interesting world. So then we went to COBOL, Fortran, Lisp, and then on up the stack. We added abstractions at each level to hide details of things. Even going from machine code to assembly language. And what's one of my favorite stories, this is way before my time, is that there was literally like controversy of having subroutines. And because the original processors didn't have a hardware stack. That was, like the little stack register that got bumped every time. That was not in the original thing. And when they added that, when they added the abstraction of a subroutine, there was controversy. It was like, real programmers don't need subroutines. They just copy and paste the instructions around, and they need that kind of control. And then the same thing there was with the goto statement, getting rid of the goto. I mean, literally the goto wars. That was a little bit before my time, but when I started programming, I used gotos. And so, anyway, so a language for the back end. Here's the things I wanted in a back end language. I wanted you to be able to pick it up fast and get some quick results, and then have a smooth learning curve as you went from a beginner into more experienced. So I wanted it to be smooth, not have a steep learning curve that you had to jump. Efficient programs. I don't like cruft. I wanted the programs that were produced to be efficient as possible. Bugs, hate them, don't like them. We can have our machines, our tools, give us a lot more help than what we currently do. When they do give us help, I don't want to stack trace, which stack traces just suck, especially with Clojure. I want the tools to tell me exactly where the problem is, so that I can stay in the flow, so that I can see that problem, that error message, and say, oh, that, fix it, move on to the next thing. And multi-threaded. That was the big thing in my career, has always been multi-threaded.
Just curious on that point, are you trying to do like pure OS level multi-threading or green threading?
In Takata, there's a pool of worker threads, and then there are green threads that are executed by that pool.
Yeah.
So this is the language checklist that, in kind of the outline of the talk. This is also a good checklist for when you're evaluating a new language that you're interested in. And we'll catch these up as we go along. Paradigms. Alrighty. I discovered this paper through a Twitter account called The Morning Paper. He posted this some time ago. Excellent paper. It's actually the chapter out of a book. And just excellent. The most valuable part is this diagram, which once you understand what's going on here, it shows what concepts you need to add to each language to move to another language. Oh, and by the way, at the end there's because there's a bunch of papers and stuff, I have a bibliography, a link to a bibliography that has all these things in it. But this lets you kind of have a taxonomy of a way of thinking of where languages fit according to the paradigms that you're used in them. And a paradigm is a collection of concepts. So concepts. Here are the concepts that Takata has. Record, procedure, which is a function. Closure, like you guys know this stuff. A single assignment. So a promise, like you can put one value into a promise, but that's it. Any other attempts to put a value into a promise fail. And then the other stuff. An agent, by the way, agent is a value that you send functions to operate on that value, and they get queued up and executed. It's basically Clojure's agent. And those functions that you send get executed in sequence. So there's a queue behind them. But here are the concepts that Takata does not have built into the core. So one of the things about elegance is how much you eliminate versus how much you put in. So these are all the things that I didn't put into the language. That some of them can be implemented quite easily, like unification. Can be implemented quite easily in a library, but they're not in the core language. So then what abstractions do you have to work with? This is where you start getting into the meat of things. Abstractions hide details behind an interface, hide details of implementation behind the interface. When you think about programming, our main task is somebody gives you a problem that's huge. We break it apart into small problems and keep breaking them down until we can solve those problems with solutions, tiny solutions, and then we compose those solutions until we get the solution. So what is, category theory is the study of composition. So that's where there's a deep well of good abstractions to draw from category theory. But you take somebody that is used to like JavaScript or is coming into things, because with JavaScript you can sit down, you can bang out some code, you get a visual effect, and then you can just hack on things. And it's a very good way to get new people in to programming because it's very tactile. But they're not going to learn vocabulary. That's really a barrier to them. So category theory, but without the vocabulary. This is an awesome paper. I wish I could understand it. But yeah, it's incredible. Highly recommend investigating that. But category theory isn't enough. It's good for composing functions, basically, but you have data abstractions as well. So here are the abstractions that are in Takata. Composition is basically just plugging two things together, two values of the same type together to get a... then containers are values that have other values inside of them. And that's where all the category theory stuff comes from, composing functions that work on these container types. Collections, your basic data, the basic way of putting data type values together. Seekables, when your collections have a notion of order. And then indexes, when you can pull one out. And then associative or key value stores, or hash maps. Okay, so let's get to the nitty gritty. The runtime, how's it implemented? There are the three basic data types, then simple containers, maybe in promise. They can only hold one value. Then you have your collections and your concurrency stuff. Okay, it's written in C. Painful, ugly, hard to do C, but I only have to do it once. Once I get stuff written in C, then I can use Takata at a higher level. And it's just pain you have to go through to get things done. It uses a reference counting garbage collection. Because the data collections are all immutable data structures that I just ported from Clojure, there are no cycles in the reference graphs. There's one loophole with agents, but if you put a cycle in your agent, you're just a bad person. And I really, you're on your own. But other than that, there are no cycles. And so reference counting garbage collection works really well, because that's the problem with ref counting is cycles. I mean, there are other problems, but regardless. However, I also wanted tail call optimization. In the naive reference counting, you have a scope, like a function body, and you increment the references as you come into the scope, and you do all the work, you get the result value, and then you decrement all the references at the bottom before you return the return value. But that kills tail call optimization. So I wanted to come up with a scheme to allow me to do reference counting, but have tail call optimization. So, and I did. I came up with a way. I don't know if it's original or not. It seems stinking cool to me, but maybe other people have done something similar, like APL or something. But the interesting thing is, in my runtime, it knows exactly, down to the instruction, when a value is no longer used. And so it can free it immediately, right then, which is pretty cool. A guy on Twitter posted a comment, not to me directly, but just in general, that reference counting should never be used. Tracing garbage collectors are so good now that we should never use reference counting, and that reference counting will always be slower. And I was like, well, I don't think so. So actually, he and I went back and forth a little bit. A very cordial, good exchange. It wasn't like your Twitter flame war. And so he posted a benchmark that he had written in OCaml that showed how good tracing garbage collection was. And somebody else did it in Haskell, and it had about the same performance as the OCaml. So this guy also did a version in Swift, and it was horrible performance, like 5 times worse memory usage, and also execution time, just horrible. So I implemented it in Takata, and the naive implementation was 10 times worse in Takata. But then I started optimizing my runtime, and I got it down to where it beat Haskell and OCaml in size of memory. I was patting myself on the back pretty hard at that point. And it almost beat or equaled the performance. And there's an issue I have that I need to add some stuff to my runtime, to my language, and I can beat them in performance too, pretty sure.
Did you write into the conversation?
Oh yeah, we went back and forth, and we actually did some private emails, and he's like, hey, what about this, and what about this? And I was like, oh yeah, and I tried things. I got nerd sniped really bad. I ignored it the first time, but then I saw it retweeted like 2 months later, and it was just too much. I just gave in. But yeah, his guy's name is John Harrop. And so we had, really good discussion and very eye-opening. And
was that idiomatic in your language? Or you said you could optimize your runtime, right?
Yep.
So does that mean that you could still write in an idiomatic way?
Yep.
And you still have the good everything? Awesome.
Yep. And then if you, and I'll cover it on the last slide, but if you do some really freaky stuff, you can really strip down the size of the executables and things for like embedded stuff. But that's not terribly idiomatic. What's next? Oh yeah, so in Clojure, we have this thing called transient. It's a keyword called transient. So you have these immutable data structures. Anytime you change one, it actually creates a new data structure that copies some information but shares structure as much as possible. Except there are times when you know that you can overwrite the old one because you're not going to use it anymore. And so Clojure has this, the programmer can put in a transient keyword and it will automatically mutate these immutable data structures for efficiency's sake. But with this reference counting, the runtime knows when it's possible to overwrite. And so it doesn't do any copying. It will, if you're mapping a list that's only used right there, it won't create a whole new list. It'll just overwrite the values in the list and keep the same structures, which really helps on memory performance. But I hope people have heard that you never use garbage collection to handle like sockets or file handles or other resources. Because in a tracing garbage collector, you never know when those are actually going to be closed because they can hang around until the next GC event. But in my stuff, I know exactly when they're going to be closed. So I can put a destructor behavior onto one of those types and free the socket right when it's done, right when it's never going to be used again. And when I did that, I coded up a little TCP server. I was like, oh, that is so nice. Given all the crap I'd done through in years before, that's another instance where I was patting myself on the back pretty hard.
Can you handle like errors in cleanup if the GC is responsible for it?
You just don't have any errors in cleanup. No. So the idea, one of the core ideas in my language is you handle as much as possible with static errors, static typing stuff, and the runtime. But if something really goes wrong, just crash. And so if you get a problem in your destructor, when it's collecting a socket, then it's just going to crash. It's just too much trouble otherwise.
Sure.
And at that point, I feel, anyway, my philosophy is you're already hosed. So, libraries. So you can use any C library, or any library with C bindings. But it's not trivial, because you have to write wrapping code around the C code. And I don't want to make it too easy to use stuff anyway. I mean, yes, I do want you to be able to tap into all the vast amounts of code. But every dependency you bring in, I mean, it's like a free software, except as in puppies. Once you get them, you have to take care of them forever. You have to make sure that there are no vulnerabilities in that library you're importing and in all the libraries they import. So there's a definite cost to bringing in other people's code. Yes, it's valuable to do, but there's a cost.
Is that static and dynamic linking?
Right now it's just statically linked. But that's really because compiler produces C code because it uses LLVM or GC. And so that kind of stuff is just determined on the when you're compiling your C code. Everything gets compiled down to a big chunk of C code, 100,000 line files sometimes, that just run through your standard C compilers.
Do you have to compile that third-party code, or do you use it as a binary?
You can use it as a binary.
Does that cause you any grief from a reference counting standpoint?
That's part of the wrapping stuff you have to do. You have to translate, the Takata data structures into whatever they're expecting on the native side.
Because you really have no idea what's going on inside.
You really don't. So that's part of why it's not trivial. There's some work that could be done to make that easier. So yeah, you can use all the tools that come with your C library. C has this nice macro that lets you do source mapping, the #line macro. And so you can do source level debugging. When I first stepped through a Takata program at the source level using LLDB, I was like, that's pretty slick. And then of course it got screwed up when I would step through the monad comprehension, but we'll talk about that later, or not. But yeah, and then you can use other tools, Valgrind or whatever for profiling, and memory profiling, whatever. So that tooling is all there for you. What's next? Types. I love types. So despite being a Clojure programmer, I have always liked, or not always, but I have an affinity for static typing. But dynamic typing is great. Again, for new programmers coming in, just want to get something going. Or if you're just not sure about the domain you're working in, you're just exploring your design space. Dynamic types are great. You can just bang out code. You can eyeball it and see if it works or not, that kind of stuff. So that's great. But static typing is also great for catching bugs and preventing regressions, especially when you have multiple people working on things. But there's a cost. Both sides have a cost. So gradual typing, try to aims for the best of both. And I like gradual typing. I like that idea. So here's 3 papers. The first one, so Jeremy anyway, he was here last year. He came out with gradual typing, I guess, originally. Then those guys at the top, did some beating on it, and they said, eh. And so then these guys came back with, so these guys point out some problems. These guys came back and said, okay, here's how you solve those problems. And then they came out with this paper, which really nails down the definition of gradual typing pretty well. The definition had been kind of fuzzy up to this point, I think. But that paper kind of nails it down. So that was all the back-end stuff. I was happy. Life was good. Progressing, I was patting myself on the back quite a bit for being such a genius. And then also kicking myself for being an idiot, depending on which day it was.
Before you go to front end, what are you targeting in that back end? Is it just like a Linux system? Is it embedded?
Any place that C will run.
Any place that C will run.
Any place that C will run. So yes, embedded, probably not hard in real time, where you have to control every single clock tick or every single memory allocation. But yeah, you could boil it down to do some embedded stuff pretty well. And any other place you can run C. Servers, native apps, whatever.
I had a quick question about gradual typing. What's the difference between gradual and optional typing?
I'm,
So like Haskell optional typing, you don't have to provide the types, is that?
like that's because of type inference?
Yeah.
Yeah. So last year I gave a talk, and actually it's in the bibliography, on typing a Lisp. And it's how the type system works. So there is type inference. The way the type system, loosely said, works in Takata is you put in these runtime assertions. They look like runtime assertions. You say assert this condition. What the compiler sees them as type information.
Is that kind of like Clojure spec?
Kind of, yeah. And so then it uses those runtime assertions that you put in or that are in the core library and infers as much as it can. And any place that can't infer types, it'll drop in a runtime check. And so it has optional typing, basically.
So do you have a cost of carrying? Do you have type erasure then?
Yeah.
You're carrying some of the runtime. So sometimes you're erasing type and sometimes you're not for the runtime?
Yes. So what happens is, so I didn't mean to get this deep into it, but at the leaves of the call tree, where it's basically C code, those are often typed. Not always, but often. So the compiler bubbles these assertions up. And if there's a conflict between a type, an assertion coming one way and an assertion coming another path, At that point, the compiler will see that and say, hey, you have a problem at this point, and here are like the reverse stacks of where these assertions came from. And then, but if it can't determine, if it gets up somewhere and it can't determine definitively that the value at that point will satisfy all these assertions, I mean, if it can, it just drops it and says, fine, we're good. But if it can't determine it, it drops in a runtime check at that point. And so all the calls below that point are erased in types, whatever. But at that point, then is where the runtime check happens. And yep.
So it is hard to use Closure without knowing Java. How much C do I need to know to use Takata?
You shouldn't have to know any. You can drop C code directly in line to Takata code. But, and that's really going to be a function of the libraries and stuff. You really should not have to know C at all to use Takata. That's the idea.
So maybe carry on from that pointers.
Do what?
How many pointers do you need to use Takata?
Pointers are evil.
Yeah. Even when you're working with other libraries, is that when you're doing the mapping layer? Like
Yeah. Yeah. When you start to use other libraries, then yes, you do need to know C and be familiar with how those libraries work and stuff. But yeah, pointers should never rear their head in Takata. I hopefully will take care of all that pain for you in the runtime. Okay, so that was all the back end. I was happy, life was good, but then WASM happened. And so I hear talk about it, and it's like, and you can compile C to it, and LLVM will do it automatically. So just on a whim, I used Emscripten. And literally on a whim, I was just like, we'll see if this works. I took the C code and plugged it into Emscripten, and it worked the first time. I was like, holy crap, a little hello world. So then I took a little program I had that I used to really stress test my compiler. And it all worked. I was like, oh crap, I guess I'm a front-end programmer now. So there are some issues, as you might expect. It's all single-threaded because of Spectre. There's no garbage collection in WASM, but I don't care because I have my own handy-dandy garbage collector. Very primitive interface going between the JavaScript side and the WASM side. You can basically pass numbers. That's it. You do get two types of floats and two types of integers, though. So you have to marshal data structures on both sides, marshal and demarshal them, going across that boundary, and translate like native types and stuff. And the WASM side, garbage collector, has to play nice with the JavaScript side. Because if you call into the JavaScript and it gives you back an object, and then you, on the WASM side, you do stuff with that object, pass it around and stuff, and then you're done with it, you have to tell the JavaScript side, hey, I'm done with this reference, so that it can garbage collect it at some convenient time for it, which just happens to be exactly what my garbage collector does. So again, I mean, when I saw that, I was like, oh man, Duey, you're a genius. So just for the younger programmers maybe that aren't as experienced, you have to be self-involved, yeah. Narcissistic, no. You have to be self-complimentary in this industry just to keep from getting really down on yourself. So when you get a win, when you do something elegant, congratulate yourself. And then when you do something dumb, acknowledge it. So what's next? Okay, so I had to write a module to cross the WASM JavaScript chasm. Had to write a module to work with the DOM, because why else would you want to run in JavaScript? And don't tell me about Node, because that's awful. Need a module to produce HTML, CSS, because you're working with the DOM. And then what about React, Angular, the other frameworks and stuff? I started looking at those things, and I was immediately just like, you've got to be kidding. This is what they do. This is what web programmers do. I mean, and it's not like an insult. I was just like, I can't believe you guys put up with this stuff. I can't believe this is our industry.
Well, this is better
Yeah. Hopefully, I'd like for it to be better.
than what it was.
Yeah. Oh, yeah. I came across this really interesting website or blog post about web components replacing front-end frameworks. So I'm really intrigued by that idea and what web components are, how you use them, how they'll interact with WASM. I'm really intrigued by that. I've not done a whole lot in there. There's also another framework called Svelte. And I saw a couple of his talks. I've not looked at it in depth, but the talks I've seen, I like what he's saying. So
No virtual DOM.
no virtual DOM, that kind of stuff. The PureScript guy also had some blog posts about you may not need a virtual DOM kind of thing. So those heavily influenced my take on how to do front-end programming. And that's the path forward for me, at least, is along those lines. And NPM, remember the puppies. I mean, every time you pull in left pad, you're just, you're opening yourself up for pain. Because you have to make sure. Anybody hear of that vulnerability where somebody took over ownership of this obscure package? Yeah, that kind of stuff. So language for the beyond. So I had the back end covered. The front end's like, okay. Then it's like, okay, so what else can we do with this thing? And so the way Takata is built, one of the goals was to have the compiler infrastructure be set up as libraries so that any Takata programmer could just use them to do stuff, like for parsing or code analysis or whatever. So they're just libraries. They're just Takata libraries. There's nothing magic about using them. So there's a library to describe a grammar, just a grammar for parsing. And then there's a library that takes one of those grammars, and I only have one right now, which is a recursive descent parser. Very simple, easy to implement, but it will take any grammar and turn it and build a recursive descent parser for that grammar. You could also take a grammar and print out an EBNF tree because it's just a data structure. The grammars are just data structures. So a parser will parse raw text using a grammar and produce an AST. And then the AST is just a set of data structures, and there's a library for working with them. So, oops, wrong button. Hello. Dang it. Uh-oh. Let's see if that'll... I hit the touchpad instead of the space bar.
Oh. Maybe it's just...
There it is. So once you have the AST, then the bulk of the actual compiler is just a code generator that walks the AST and spits out C code. Of course, it's much more painful and ugly than that, but that's the basic idea. So what if we did something else with the AST? In this case, what if we executed it directly and basically interpreted the AST? And so I think I was driving my car when this kind of gelled, and I was like, oh, I could have an interpreter. Cool. How hard could that be? Anytime you ask yourself, how hard could that be in programming, you're in for pain. Because you're not fully aware of what the problem is. And so this was my case. But anyway, yeah, it should be easy because all the grammar and parsing are in libraries. And the compiler already has them. So the compiler executable already has these things in it. So adding just another module to my compiler would give me an interpreter. So like a shell script, like bash or whatever. Just put a shebang at the top of a Takata file, and you have a scripting language. How hard could it be? Well, so in the interpreter, you have the compiled code, like the core library, that's already compiled into, say, the compiler. And that you don't want to reload that stuff on the interpreted side in an interpreted version. You want to make use of that compiled side. So you kind of have these two sides. You have the compiler, the compiled code side, and the interpreted side. So in the script, you say you define these three functions. Everything's fine. They're all on the interpreted side. You can interpret the ASTs, make the calls. Everything's lovely. No big deal. Until you try to call a compiled function. So it's like, okay, well, I got to deal with that. Okay, that's not too bad. I can export symbols and make them available at runtime, and I can do stuff. And so I got that done. And so the interpreted code could call functions in the compiled side and get the results back, and everybody's happy. It's all good. So then, what if you call a higher order function on the like a compiled higher order function like map, with a function that is defined on the interpreted side that can't be executed, it has to be interpreted. So what do you pass into that higher order function? You have to pass in all the context that is needed to interpret that function at that time. But we're functional programmers, so we can do that. So yeah, it creates a thunk that closes over all that state, passes the thunk in to the higher order function, which then just executes normally, calls back the interpreted side, which then can call back into the compiled side. So effort, but doable. Not too bad. So Takata has protocols, basically type classes, interfaces, whatever you want to call them. So if you define them on the interpreted side, define your protocol, then define your types that implement those functions, these are all interpreted. And so a call site down in foo for bar is just a normal call site to an interpreted function that looks up by the type, and everybody's fine, happy. It's not too bad. However, there are protocols that are defined on the compiled side. And so at the interpretation time, you implement a type that implements those functions. You have to extend those functions from the compiled side into the interpreted side. But compiled functions like print error right here call those functions. And you have no idea where those call sites are. You have no access to them. They're locked away in the compiled side. And when I hit that, I was that was one of the times I go, you are an idiot. But being able, when you write your own compiler, you can do stuff. And so I did stuff. So anytime there's a call site, when the compiler sees a call site to one of these prototype functions, it puts some other code there which says, oh, by the way, if you're running in the interpreter, check this other thing before you give up on trying to find an implementation for this particular function. And it works. Except if you go back and forth in some weird fashion, the reference counting garbage collection gets screwed up. That's my current bug that I've got to track down. And it is looking like it's going to be really painful. But it's only going to be like a 2-line. The bug is only going to be like 2 lines. It's just finding those 2 lines. So that is kind of the stuff that comes up when you're trying to go beyond your normal compiled side of things. But once you get that, you can do cool stuff. So I do have the interpreter mostly working. So I wrote a little script that you pass it the file name to a Takata source file. It parses that file, picks out the imports of other modules, then parses those and does a recursive descent. And this is the dependency tree of the modules of the compiler you visualize using GraphViz. So it's just a little script, kind of a proof of concept thing, and it works, and it's beautiful. And when I'm hacking on stuff and I update various modules, and then make new Git commits, their SHAs change. And so who needs to be updated with this new SHA? And so this gives me a map of, well, if I update stream.talk, then I need to update shell and file and all the stuff. Yeah. And so that's, so you can use stuff like that. You have the ability to script the compiler to write tooling. And you just put a shebang at the top. Or if you want it to execute really fast, you take the shebang off and you put some other stuff in and compile it. And it's a native executable. You don't have to change your code. So with all that, using WASM, we should be able to run like serverless Lambda, AWS Lambda functions, I would think. Doing some compiler directives at the C compile time. You can strip the binaries down to make it like for embedded side of things. Because my first love is always going to be embedded, you know, just the way it is. So kind of summing up all this stuff, it really seems like, in my experience now, that these concepts, this handful of concepts, with being available through these abstractions, really is a sweet spot for language design. You can definitely go beyond it, and for certain cases, certain things, you can you need to. But for the way we do programming now, this handful of things really is about all you need, I think, with support like typing, static typing, gradual typing. We can do it a lot better than the language that we're currently using, and bring new people in faster, get them to be able to do useful work for their own lives more quickly, without having to learn immense amounts of stuff that we take for granted. And it's a small enough piece that we can, it's understandable. So that's my rant. So the website, the Twitter handle for the language, and then the bibliography for with links to all the papers and blog posts and other stuff that has influenced my thinking on this. And I can tweet the slides if anybody wants that, or send you an email or stuff. I'm not on Slack. Sorry. Talk about cruft, your machine slowing down, using gigabytes of memory. So that is my rant, my talk. Questions, comments? Pardon?
Macros?
Funny enough, I have not found a need for macros yet. I am not necessarily opposed to them. They're just going to take effort to put in, and I have better things to do with my time so far. At some point, I assume I will, but yeah.
Multi-methods?
Probably not, unless, the way this goes, I'm not opposed to doing anything if there's a reasonable case for it. And unlike Clojure, where you have to do a CA, contributors agreement, to make contributions and stuff, and then go through a whole,
Which they may or may not accept.
Huh?
Which they may or may not accept.
Yeah, exactly. If anybody ever wanted to make a contribution, it's like, okay, this is yours now. Especially if anybody made a contribution to a library. It's like, all right, you're now the proud owner of a new library. So anyway.
As a library, it should fit nicer. Like if I wanted to run like an Apache module to Kata, any concerns?
I'm not familiar enough with Apache to really answer that, but I'm going to say no concerns at all.
Okay.
How hard could it be?
So I could make a C library with exports, and it'll work like everything else in Raw.
Should be, yeah. Alrighty. Thank you guys and Charlene for coming. And,